All right, so now that we've seen a little bit about transmutation and a little bit of what goes on with nuclear chemistry, let's look about writing some of the equations. So looking at this, a typical chemical reaction, we haven't gotten to those yet, but this is what it looks like. You've got H2 plus O2 equals 2H2O. So the left side of the equation lists the starting material before any change occurs. And then the right side is what happens after the fact, like the change occurs. The arrow right here represents the change. Any reactions show a conservation of mass and charge. So hydrogen right here, there's two of them, 2 times 2, there's 4. So there's 4 right here. There's only 2 here. They're on the left side. On the right side, there's still 4 here, and there's the O, and there's the 2. There's still 2. There's no charge, no charge. Okay? Nuclear reactions will appear to be slightly more complicated, but follow the same basic rules of conservation. Whatever you have on this side right here, has to equal what you have on this side. Okay? So nuclear decay. When writing decay reactions, predicting the products, we're going to classify nuclear reactions. We're going to predict the mode of nuclear decay. Okay? So the nucleus is too big. So if that nucleus is too big, and like say elements greater than 82, remember that strong force becomes ineffective because the protons are too far apart. The quickest way to reduce the size of the nucleus is through an emission of an alpha particle. Remember, that's the biggest one. It's worth 4 according to table O. The alpha particle right here is a helium. So, for instance, let me move myself out of the way. Americium-241 will decay through emission of an alpha particle. So you have, Americium and the alpha particle. The upper left number is the mass number of the particle right here, 241, and there's 4. So remember, whatever's on this side has to equal on this side. So looking at the alpha particle, we got 2 protons, 2 neutrons with a mass of 4. We're also going to put in the atomic number on the bottom. Need that. It's a necessary. So we got 241 up top, 4 up top, 95 on the bottom, 2 on the bottom. We gotta have the charge of the particle. That's the atomic number. So the mass numbers and charge numbers must be conserved. Whatever's on this side has to equal on this side. So whatever's on this side of the arrow has to equal this. So looking at this, this side has to equal 241. So 241 minus 4 equals 237. 95 minus 2 equals 93. Now all I have to do is look up on my periodic table, what is 93? 93, where's my 93? 93 is right there. So there's my 93. And this is alpha decay. All right? So this, because it's so big, is just going to shoot off an alpha particle. And when it does that, it's going to shoot off an alpha particle and a, oh good Lord, I don't know how to say it, NP is going to be neodymium. Neodymium. Oh, no, is that neodymium? No, it is not. Sorry. Neptunium. Neptunium. Because I can speak. All right. So some more alpha decay. So this is 263. So looking at this again, typical for large nucleus, anything over 82, it reduces the size of the nucleus. The fastest way it can do that, get rid of the biggest particle. That's the alpha. So when I have the 4 and the 2, 263 minus 4 is 259. 106 minus 2 is 104, giving us our F, which our F is 104. that is rutherfordium. Okay? So small elements up through the atomic number 20 are most stable with 1 to 1, right? So this is perfect, this is perfect, this is perfect. That's where they want to be. They're very, very stable. Larger nuclei need a few more neutrons as a buffer between the proton and the positive protons. So it requires 1.5 neutrons to 1 proton. Example, darn it, 74. I know I want to say it's tungsten, if I'm not mistaken. I am right. Tungsten and plutonium. That makes them happy. This is their stable spot, right? So they've got this many neutrons to that many protons, and that's what it wants. Correcting the ratio if a nucleus has too many neutrons. So like carbon-14. It has 6 protons, 8 neutrons. To correct this ratio, a neutron is converted to a proton by emitting an electron or a beta particle. See, there it goes, bye-bye. And now it is a proton. I can do that again. So watch this neutron. It's going to emit that electron or beta particle. There it goes. And it turns into a proton, and it makes everything happy. So a nitrogen 14 has 7 protons, 7 neutrons. This is naturally transmuted to become stable. Since the electron has a negligible mass, the mass of the nucleus is essentially unchanged in beta decay. Because what happened right here? We took a proton, we got rid of a proton, and we turned it into a neutron, right? And when that happened, we changed the number of protons. When we changed the number of protons, we now change to we gain 1 more proton to make it nitrogen. So everything is happy. All right, so that is it for right now. If you have any questions, please don't hesitate to ask. And I hope you guys have a great day.